Hello everyone and welcome to homework help video for lesson 6.1. We'll be solving exponential equations and doing some parts of 1, 2, 3, and number 4. So let's jump into our notes. In order to succeed in this lesson, you need to recall our old exponent rules. The first one right here says, hey, when I have two bases being multiplied together with different exponents, okay, but the key thing here is that the bases are the same. Then we will add the exponents together. On the other hand, we have another major rule which says, hey, when you just have one base, notice the difference. This time I only have my base written once, my base here being x, and it's being taken to the power of m, and that's being raised to another power. I like to call this the power to a power rule. Then you're going to go ahead and multiply those exponents. So it's going to be x to the m times n. So be very familiar with these formats and when to add the exponents and when to multiply them. Now, what we're learning new in this unit is that if we have something in this form, b to the x equals b to the power of y, and notice how the bases are the same, well then we know that our exponents must be equal to each other. So x has to equal y. Notice my exponents, I've set them equal to each other. So this is actually super straightforward. It's like if I said 5 squared equals 5 to the x. Notice that since my bases are both the same, they're both 5, that means for this to be true, right, for the left side to equal the right side, x has to equal 2. That's the only way that this works. Because if x equaled something different, like 1, obviously 5 squared is not equal to 5 to the 1. Or if it was something different like 3, then that's not true anymore. So as long as the bases are the same, then we can say in the next step, our exponents are equal to each other, and so x equals 2. So the goal then for all of our problems is first to find a common base. And once we do that, we'll set the exponents equal. So let's go ahead and look at our problems. Problem number 1. So here's the bases that I'm looking at. Right now I have a 2, and I'm interested in this 4 here. So between 2 and 4, both can be rewritten as powers of 2. 2 is just 2 to the 1, and 4 is 2 squared. So I'm going to handle this. In my next step, I'll rewrite these both as powers of the same base, my base being 2. Okay, but we're not quite done. We're not exactly in this form yet. So notice that this fraction is getting in the way. Next step is I'm going to remove the fraction using negative exponent rules. So to get rid of this fraction, I'll rewrite it in the next step as 2 to the power of negative 2. Recall that a negative exponent means you're going to take the reciprocal. So it'll turn it into a fraction. So just add this to your notes. 1 over a to the power of n is the same thing as a to the power of negative n. And that's what we've done here. We took 1 over 2 squared and made it 2 to the negative 2. Well, now I'm happy because my bases are the same. And if my bases are equal, that means my exponents must be equal to each other. So next step, I'll set my exponents equal, ignore your base, and we have x equals negative 2. Okay, let's do the same with problem 2 now. So I'm interested in 8 and 32. I want to rewrite them as powers of the same base. Both 8 and 32 can be expressed as powers of, if you said 2, then you got it. Because 8 can be written as 2 cubed to the x plus 1. And 32 can be rewritten as 2 to the 5th power. Now I have some work to do. Notice that we have this power to a power. That means using our rules from earlier that will multiply. So in my next step, I'm going to rewrite this as 2 to the 3x plus 3. Notice that I distributed. I had to multiply these together. Equals 2 to the 5. Next step, I'm glad that my bases are equal, so I can now ignore them and set my exponents equal to each other. 3x plus 3 equals 5. Solving for x, I'll get 3x equals 2. And in my final step, I'll have x equals 2 over 3. So once I got to this step here, it was all basic algebra to the end. Let's start with our third problem. So now I have something interesting which you may have seen before, you may have not, but this number e, this is actually a number. It represents something like 2.7 with a whole bunch of decimals. Right? It's just like if you see pi, you know that that is approximately 3.14. So just know that e is not a variable we're solving for, it's an actual number. With that in mind, I'm just going to ignore the e. I'm going to treat it like as any other number. It could say 3 everywhere for all I care. So don't be bothered by that. Let's just continue with the problem. And so notice that I'm not in this format yet. The right side has too many factors. I need to condense this into just one exponential expression. So if I want to condense these guys into just one term, then I'm going to have to use the rule that says to add the exponents. So next step, I'll condense the right side so that it says e to the x squared, and I'm adding the exponents, so x squared plus negative 2 is x squared minus 2. Now, look at the left, look at the right. We have our bases already in common, so we can set our exponents equal to each other and do our algebra from there. Notice that we have an x squared. That means that we're going to need to factor this, right? Solve by factoring. But before we factor, we move everything to the same side. Right? Set it equal to 0 so that we can factor and solve. So to get everything to the same side, I'm going to move this guy, this x to the right. So minus x on both sides. Line it up with its like terms. There are no like terms. So on the left, I'm left with 0 equals x squared minus x minus 2. I'm going to factor this now using magic x. I need two numbers that will multiply to negative 2, add to negative 1. Try it yourself. Check back with me when you're done. And I'll see that I have x minus 2 and x plus 1. That means I have two solutions to this problem. X equals positive 2 and x equals negative 1. So that last problem was a little more complex because we had to do some condensing on the right side first. And then once we set our exponents equal, we had to factor. So a little more complicated, but still it's just following the same two steps as before. We can handle anything. Let's do the last problem from our homework. So this question asks us to compare the left and the right side using less than, greater than, or equal to signs, operators. So I'll show you how I would go about doing this problem. On the left side, I'm going to take care of my negative exponent. Remember, negative exponent means we're going to take the reciprocal. So the left side really becomes 64 over 1 to the power of 1, which is just 64. And on the right side, 8 to the negative 2 becomes 1 over 8 squared, which is 1 over 64. So now it's easier for me to compare. 64 on the left is clearly greater than 1 over 64, which is a small decimal. So we have a greater than sign. Let's do the same thing with e. On the left, e to the 6th stays as is. On the right side, we have to use some rules. So let's condense. When you're multiplying with the same base and then different exponents, we remember to add the exponents. So that's really e to the 6th power. And if you don't believe me, check it out. This is e to the 5th times e to the 1. Isn't that e to the 6th power? Yes, it is. Convince yourself. that these two sides are actually equal. All right, last problem. 10 to the negative 6, that's 1 over 10 to the 6th power, compared with 10 to the 4th, which is 1 over 10 to the 4th power. So here's what's really going on. If I have 10 to the 6th, I have 10 times itself 6 times. That's basically 1 in a million. Whereas if I have 1 over 10 to the 4th, that's 1 over 10 times itself 4 times. That's 1 in 10,000. The guy on the left is much closer to 0. It's a smaller decimal. It's like 0.00001. Whereas the guy on the right is 0.0001, if my math isn't wrong. But the idea is the larger the denominator, then the smaller the number, right? So let me make a note of that. Larger denominator equals the smaller number overall. It's like if I said, would you rather have a half of a pizza or a half of $1,000,000 or 1 out of 10? I would much rather have half, because 1 out of 10 is just a really small piece. So the larger the denominator, then the smaller the piece. So in this case, since on the left side my denominator is so much larger, that means it is a smaller number. I hope that you found that video helpful, and I'll see you next time.